what I want to talk about is a bunch of different models for how to think about data structures in Filecoin, and a lot of notes of what is going to change and you should not rely on. So if you're using those abstractions, you're going to have a bad time. I had this kind of conversation with a lot of people 2, 3, 4 years ago, and the prediction track record is pretty damn good in terms of things that we're going to have a bad time. So, for example, you should include both PCID and the payload CID into the deal, or you're going to have a bad time. We didn't do that. We didn't make it optional. We're now having a bad time. All kinds of things like this. And so what I hope to do through this talk is give you a model for why some of these things are important and why you should be very careful about crossing layers of abstraction. If I can do that, if I can motivate, be very, very careful about crossing layers of abstraction, then it will be a successful conversation. Cool. So what we're going to go through is we're going to map systems first and kind of understand the range of things to deal with. Then we're going to go through the layers of abstraction. We're going to talk a little bit about data structures on chain, because that's coming fast. We have very few data structures on chain right now, but we're going to have a lot more very soon. And we're going to then discuss some things that are very likely going to change, and then if there's time, we can talk through other notes. My guess is we're going to spend 80% of the time on the layers of abstraction part. Cool. So this is the one way to map the Filecoin system. You can think of this broad structure where you have storage clients and retrieval clients. They're often the same parties, also often not. So they're kind of separated out here to show the storage and retrieval lifecycle. You usually have a whole set of software, products, services that are on-ramps that are tuned for specific applications, that tune the data structures and the tools and so on for a specific use case, onboarding the data into storage providers. And then on the way out, you have retrieval clients trying to get the data, again, through a set of on-ramps or off-ramps, depending on how you want to call it. And those different structures also tune the retrieval story for the specific application. Often, it'll be very common that the same piece of software does both the storage and retrieval part, and that's fine. But it's useful to separate it out here to know that there needs to be some indexing along the way and how it fits with other types of retrieval clients. Because it won't just be the single set of users that you're working with that are going to end up retrieving that data. So you can think of the store and retrieve cycle this way. Indexing kind of looks like this, where there's all kind of parties that could contribute to the indexing. Today, we primarily build the index out of storage providers and some of the on-ramps. And we retrieve the index usually in the retrieval provider component, namely things like the gateway and the FS gateway and so on. But you can think of the index as being able to be updated also by clients as well. You should get ready for a world that has a lot of computation all over the place. So computation will start going into many different layers of the stack here. The computation will come into the SPs, and computation will run over the data, produce more data. Computation will come to the retrieval providers as well because of edge functions and so on. And there likely will be computation applied in the client side as well. So whatever data structures you think you have today, you should expect and assume that a lot of them will mutate in the future. And so don't build things that you expect not to change. Just to get clear on what changing a format does, I just did a quick search on GitHub for IPFS, and there's apparently 13,000 repositories, and the code number didn't load. So of course, most of those are probably forks of some normal code bases, and most of those are abandoned. But just so you get a sense of what happens when you go and update or change some data structure, some format, you then break tons of software everywhere. This is the real reason why Git is stuck in SHA-1. It is not because Linus and others are obstinate. That's a kind of rationalization that like, hey, we were right all along. It's because changing the hash in Git, because there was no self-describing, would break so much software that no one wants to do it, even though it's insecure. And the people that are worried about security then have to patch it and live in this fragmented state. And that oversight is what led to things like multi-hash and things like that, to be able to self-describe things. One important lesson we've learned over the last 10 years of building these systems is never going to change should be considered harmful. Always self-describe. Whatever you think you're doing, where you have some code that could vary, self-describe it. Just pay the extra cost in a few bits to self-describe the thing. You will have a great time if you self-describe everything, because then it is very precise for the programs that will come in the future, that component is likely to change, that it could be variable length, that the thing you're pointing to might have some other types or whatever. Just self-describe all the things. All over the place, wherever we found thorny, really bad problems, most of the time it could have been fixed by another set of self-describing bits earlier on in the stack. So if you self-describe, then you can mutate with confidence. You can change and evolve systems with confidence, because when you change the thing, all of the other things don't break completely horribly. They just stop working with some of the new stuff. But they don't kind of horribly break and catastrophically fail, and you don't kind of lead to an incompatible mess. Here's another way of looking at systems. This is a set of kind of layered networks. You can think of the libp2p network as the biggest network that all of these systems are part of. Actually, no, the internet is the biggest, not pictured here, is the biggest network that all these things are part of. As a subset of that, the libp2p network is a network for a lot of different systems that a bunch of things are built on. Then a subset of that, the IPFS network, uses libp2p to build this data addressing and distribution mechanism. And as a subset of the IPFS network, the Filecoin network adds some incentives and other structures to be able to have a very large scale content addressing set of services. And so, when you think about like the relationship between Filecoin and IPFS, that's kind of the model that you should have in mind. Filecoin is a subset, it's a subnet of IPFS. And you can think of IPFS as the protocols that that Filecoin uses to address its data, to model its data, to move around the data. So whenever people talk about like compatibility between IPFS and Filecoin, that's like a misnomer. That's like, please like don't do that. It's Filecoin nodes might model their data in the IPFS way, or certainly model the data in the IPFS way, and move around the information in the IPFS way. That's kind of the description. Any questions about this? Because this is kind of like a source of just an enormous amount of confusion, and so I want to like let this sink in. Cool. Yeah.
I want to ask, when you say Filecoin nodes may model their stuff in the IPFS way, at the same time you're saying
like
nodes
do like always do, or all of the content address data that we have. So the blockchain itself, the state tree of the blockchain, the payloads, the sectors, all of it is meant to be content address,
So
IPLD.
So the right statement is basically Filecoin already is an IPFS implementation just by design.
Correct.
Okay.
Yes, by design.
That was Peter from Things.
Sorry, and that includes, on your work on data onboarding, that includes data transfer protocols as well.
Yes. Yeah.
Well, consensus and non-consensus data transfer protocols work.
Mike, please.
Yeah, Adine, I work on IPFS related things. Yeah, this is true with both the consensus and non-consensus chunks of Filecoin transferring of stuff uses CIDs to verify things when possible, right? If the thing is mutating, not immutable, no content addressing.
Yeah.
But when it is, yes.
If I write today an HTTP protocol, like a client, an HTTP API, and I write a client and a server that communicate objects, and I check the CID, and I request something by CID, and I get back an object, and I hash it, and I verify it before I return it to the application, that's an IPFS implementation. Like, that's the model you should have. If you're using CIDs and content addressing and moving around bits that way, that's IPFS. That's what IPFS is.
But it's not like going specific around bit swap is IPFS or crossing is IPFS.
Or lib2p even, for that matter.
Or lib2p, yeah. There is a discussion about the fact that if lib2p does not support native vanilla HTTP, then IPFS will have to evolve to include the HTTP stack without lib2p. And I think the lib2p team right now is kind of implementing a lot of those that tooling so that that doesn't happen. But yeah.
Arkady Kukarkin, Internet Archive. So it sort of feels to me like you're conflating networks and concepts. So here in this slide, it appears that the networks are subsets of one another, but what you're really saying is that the concepts are subsets of one another, because the networks do not share DHT. They, until recently, did not actually communicate meaningfully. Retrievals were not possible from an IPFS node, et cetera. So I don't really.
No, but so that's the confusion that I'm trying to dispel. So I do explicitly mean both the concepts and the networks. A lot of people think that the IPFS network means the public DHT. That's not the IPFS network. That's just one network. The same way that there is the AS system on the internet, and that's one part of the internet, but it's not the whole internet.
Well,
So, and then Kubo is not IPFS. So if Kubo couldn't talk to Lotus, that doesn't mean that Lotus isn't IPFS or that Kubo isn't IPFS. You should be thinking about implementations and software being compatible, not Filecoin and IPFS. Because you should think of Filecoin as being an IPFS implementation wholesale. And I know that this is confusing, and I know that this has been written about everywhere. Like, there's tons of blog posts that I've been trying to go around correcting for like 2 or 3 years now, and it sucks. But that is the case. All in a bunch of protocols everywhere, we are moving and evolving the stack around CIDs and distribution of CIDs, and that may or may not come to Kubo. That may or may not come to specific implementations. That's kind of up to those implementations to support. The gateway, for example, returns certain things that Kubo doesn't. Like, and yeah, it'd be great for Kubo to find it, but so I do mean the concepts and the networks. And so think of the IPFS network also as like, if I set up a private IPFS network here using Kubo or some other thing, and I just connect to the laptops here, that's an IPFS network. I don't have to connect to the rest of the world. It's just that the Filecoin network happens to be a large-scale, mega-connected network. It does not have like the broad partition tolerance that IPFS does yet. I don't know. Did that help? I don't know. Or feel free to like ask again or something, because it's super, super useful. I'm like,
it's not that I don't understand. I guess it's that I feel like you're talking about a network versus the network somewhat interchangeably, and there is certainly a dominant global, fairly connected IPFS network. That is from a user experience point of view, that is certainly an important concept that I don't find that just setting it aside is very useful.
well, so think about HTTP, right? So if I create an HTTP server here and you start requesting things here in this network, and we cut the cable to the rest of the world, is that HTTP or not?
That's HTTP, but that's not the internet.
Is that the web?
Right.
Is that the web or not?
It's not the World Wide Web. Like,
No, but it is. It is part of the definition of the protocols. That is web standards. It's using a browser. It's communicating to servers.
those are standards, but no one would say that network is on, quote, the internet, right? In a non-technical, regular person kind of way, right? Because
But it does, and it happens whenever a country loses connectivity to the rest of the world for a while. A huge fraction of the web in that part of the internet works just fine. The internet is not a single connected thing. The internet is a network of networks that constantly partitions and has tons of private networks that are sometimes air-gapped fully, sometimes transiently air-gapped.
I guess I would just argue that the network of networks that is the internet is more able to talk. Any node is more able to talk to another than what we've had for like Filecoin and IPFS for some time. I mean, it's like I don't know.
Yeah, it is great and very valuable when the networks get as big as possible and as interoperable as possible, and that falls out of just network theory of like the utility of the network increases when where more nodes can talk to each other, and so we should aim for that. But the model has to account for the fact that you have disconnected environments, that because of physics and speed of light and propagation of information and devices and so on, you absolutely will have all kinds of partition environments, or private environments where users choose to segregate their data or their devices from others and not connect them for access controls. Like we will, if we get to it, we will talk about what will likely be private subnets of Filecoin in the future, where some users don't want their interaction to be visible to the whole world. So yeah, this is I understand that this is like a very annoying concept given a lot of the writing that has been done over the last few years, but it's kind of an important one because it helps break some of the expectations that it helps break like some of the conceptual like blocks that we've had along the way. Yep.
Can I try to maybe dig a little bit further down? Are you effectively saying that a network is something that could communicate as opposed to something that does communicate? So for example, going back 40 years, right? As long as you have a POSIX machine, you can kind of make it talk to another one. Doesn't mean that they talk right now.
Correct.
The same way we're talking here about arranging data and metadata in ways that could be connectable, just like two Git repositories and two laptops can talk to each other, doesn't mean that they do talk to each other. Yes?
Yes. So like the internet, like the web, it is fragmented and ideally and hopefully fully routable globally at all times, but that's something that is best effort. So it is not guaranteed, but it is best effort. All right, cool. I'm gonna move on a bit because the meat of what I want to talk about is here. So let's talk about layers of abstraction for a moment. This is part of the famous pieces PDF that a lot of people talk about. Here you have, on the left side, a whole bunch of different data structures from different sources mapping into IPLD graphs and car files, and then eventually going into pieces and so on. I just use it as a reference point of like the kind of thing that we're going to talk about. We're going to look at a more expanded version of this in a moment. And we're going to do it part by part. So part one is what the user cares about, the user's data. This is not the user's files or databases. That's later. This is what the user cares about. There's usually some bits of information. There's relationships between data. There's stuff. There's information that goes into documents, information that goes into pictures, and so on. There's like, this is very, very abstract, but that's ultimately what the user cares about. The user cares about that data. The other stuff that the users tend to care about is how you implement that in a system. So the next step after that is the user file system or operating system or database set of structures. So stuff tends to get put into files, and then those tend to get organized into file systems. Data relationships tend to be put into databases or key value stores or whatever. Databases get put into file systems, and file systems get put into databases. So thanks to 60 years of hard work, all of these things tend to be highly interoperable. So you can take one and put it in the other, and so on. Now, there of course software will be there'll be trickiness and inefficiencies and so on. And there's lots of different kinds of these sorts of things. But this is what the user applications end up using. It's not what the user cares about, really, but it's what the applications end up using. And there's an enormous amount of work done to create a lot of portability here, but even this is highly fragmented, right? So all kinds of formats and systems don't really talk to each other. There are conversions all over the place. There's lots of functions that you have to run and write and so on. And here I'm compressing probably, I don't know, 5 to 10 layers of stuff, right? So if you really kind of were to be very pedantic about it, this single layer would probably expand out to like 5 to 10 layers of different layers of abstraction in there between like what the user really cares about and how it's represented in their systems. Like the application is probably writing a file into a file system. The file system is probably virtualized on top of some other thing. That thing is on top of a drive. That drive is part of like a very large disk partition. This partition is probably might be part of a distributed file system. Like there's all kinds of layers in between, but there's an enormous amount of work to kind of make that highly portable. Cool. The next layer is IPLD application graphs. So these are not just like the raw IPLD graphs. We haven't gotten there yet. This is translating the traditional world of files and file systems and databases and so on to content address versions, to persistent data structure versions, to hash linked things, to things that give you the properties of decentralized systems. This piece, in a big way, we're trying to kind of create this subset of the user-FS operating system structs that have content addressing because it gives you like this extremely valuable property while enabling a lot of interop and conversion. So we want to be highly, highly portable with all the other things, and we want to enable lots of round tripping to happen, because if we can do that, then the users are going to be really happy. But at the end of the day, you're kind of taking some other set of systems and mapping them into the content address model. The more successful we get with this, and the more data there is like this, the more this set of data structures are going to sink down the layers of the stack and are going to become part of the sediment of the systems. The same way that things like Unix path names have sunken down into the systems, the same way that URLs and things like that have sunken down through the system. The more data there is that's content addressed with CIDs, the more these data structures are going to percolate through the rest of the layers, and the more software will exist to make it really neat, really useful, really fast, and so on. And we have more and more kind of mappings from one set of systems to another. Any questions so far? We haven't even gotten to CIDs yet. Yep. Or rather, these things use CIDs, but I'm explicitly kind of putting that aside.
Massey, I work on content routing and content onboarding. Juan, are you not concerned about the need for efficiency to map the user file system OS stuff to the IPLD graphs?
Of course, but I mean, so are the designers of the file systems on this computer, and how many layers of abstraction are there between this Keynote file and the like electricity on the computer?
Right, but we're talking about physical separation here, right? We're talking about a network of nodes that may have fraction of CIDs scattered across multiple machines, and
yeah, in the same way that there's a network of machines with scattered POSIX file systems all over the world, and many of which don't interrupt that well.
So what are your thoughts on introducing a layer of IPLD graphs while maintaining, or hopefully, I think we all want that, outperforming the existing abstractions?
I think that is fundamentally not only possible, but part of the goal. It's just that right now, we're starting with a much smaller fraction of the data, and there's tens to hundreds of years of software to write, which you can do with a lot of people, but hundreds of years of software to write to get these things fast. Like when you look at a bunch of these systems and you try to analyze how they got so fast, and then you look at how big the software project is and how long it's been running and how many contributors it has, some of these things have like thousands of years of human time poured into them to make them that fast. And so wherever possible, we should be trying to do that. And by the way, good news, like because the Filecoin network is so big and requires so much hardware, a lot of the hardware providers themselves are excited to do some of this stuff. Like I've been in tons of conversations about bringing CIDs and even some of the guts of Filecoin into drives themselves, so that you now have like some of these concepts directly in drives. There was a big effort by a few different companies. I think Seagate did this, and I think others might as well, to bring content addressing to drives. There was kind of like an attempt that didn't work because the applications didn't use it yet. So it tends to be that new abstractions follow application use. So you have to get a new abstraction to be highly used by some set of applications, and over time that then percolates through the layers of the stack. The stack doesn't really evolve because it's better to evolve it. The stack evolves because the applications demand it, right? So there's been tons of proposals for changing guts of the internet and so on, and they, think of like the IPv4, IPv6 problem. All of this tends to follow application use and the momentum of software, and kind of the deployment of all kinds of pieces everywhere. And so to get to that efficiency that you're talking about, which is not just possible, like the goal, we have to get it highly adopted. And then over time, more and more solutions will emerge. But yeah, wherever we can do that, like that'd be great. Good exercise to do might be to like peek on their high performance systems and figure out whether you can like sprinkle some magic IPLD dust in there to make those systems as they are suddenly be content at rest capable, right? So like go look inside Postgres and see, can you like IPLDify it? Or go look inside some other file system and see if there's like a clean mapping. Because then that way you leverage the high performance systems that have been already built. That's a great question.
Thank you.
And one of the pieces is like, think a mental model you should have is that software accretes, hardware gets replaced. So even though the world of hardware intuitively we think that software is more malleable, it actually isn't like that. Software is way harder to kind of get rid of. And so you start accreting all software that just still expects things to behave a certain way, while hardware tends to get turned over quite quickly. So you can get something adopted, and once it gets adopted in a bunch of places, then hardware will evolve to optimize the hell out of it. So you just kind of have to get large-scale adoption of something. And by the way, having exabytes of data formatted a certain way kind of qualifies. One question here is, note that I have Git repos in there and blockchains. We designed CIDs to be able to point to all of these things. So it means that we don't currently have a bunch of software written for this, but you should be able to take Git repos as they are and dump them into car files and put them into Filecoin, and then later start addressing them on chain. So kind of where we're headed is like you'll be able to have a notion of a Git repo on chain and permissioning on chain, pointing to the description of a Git repo, and store all of the objects inside of the deals, and then be able to have like Git clients that just interact with the chain directly.
So Juan, actually, I have a question regarding what you were just saying in response to my C's question. So we've been trying for many years to get other organizations and projects to adopt IPLD style content representation, including some extremely highly value aligned ones like Nixos is a perfect example. And that has gone on for, I think, at least 5 years, and not much progress has been made. So I'm wondering what you think the big blockers are there.
Yeah, great question. I think that it is unfinished software and like not enough good implementations of the IPLD libraries, and we're missing some. I don't mean to get into this, but a lot of the utility comes from being able to easily represent data structures. So we're missing kind of like a protobuf style piece of software that can very easily enable an application to describe its data types and then serialize, deserialize, transport, and so on. And IPLD schema try to get there, and I think it's a really good, it solves a bunch of like hard problems, but it's not good enough to be as easy to use and intuitive and kind of like low barrier to entry as protobuf is. Or we would have seen that adoption happen today. And think of like just as an example, just try thinking of a very simple set of data structures. Think of Git, like implement a very basic version of Git with like blobs, trees, and commits, and try to write it with IPLD schema, and then try to write it with protobuf and see which one's easier and why. And like that's a good test case for like why we haven't seen that adoption happen. I think there are also some kind of documentation issues. Like there's, I think right now IPLD is just not a very approachable project. It's very kind of convoluted, and it kind of like suffers from the same thing that the semantic web sort of suffered, which is kind of like concept astronomy, where like suddenly you get like sucked into the ether of like all the different kind of potential concepts, and so it becomes pretty hard to understand the concept space. And so we need like a super, super basic version of it, kind of what like schema.org did for the semantic web, where schema.org was like a super simple that like get like 80% of the value with like, this very trivial set of data types and so on, and pieces of software, and you can get like really far with something like that. And so I think we're kind of missing that sort of thing.
I want to just, I guess I want to address like a little bit related to that. I think Git specifically, we can actually go and import and carify and whatever all the data, and I think there are actually IPLD schemas, I feel like, that were written a few years ago that will do that. Part of the difficulty has been around basically the fact that when you're addressing systems as they exist today, their data is going to be shaped in ways that maybe some of your existing systems aren't prepared to deal with. In our case, this is block limit things, right? So a lot of our protocols is a function of wanting to operate in peer-to-peer and untrusted systems. They don't want to have to download 1 exabyte of data before throwing it through a hash function and seeing if it matched, right? They want to work with smaller, discrete values. And that's what's caused that's been some of the big problems with working with Git data. Aside from the fact that not a sufficient number of places have the Git secure hash function that would make it so that using Git that way wasn't a bad idea, as Linus says.
Yeah.
But this is part of the adoption thing. Is that I feel like, I don't want to totally derail, but like having support for large enough for saying, yep, the blocks can be bigger, and we can figure out how to make them work, because if the IPFS space is anything addressable by CIDs, then the things addressable by CIDs need to allow to be arbitrary size.
Yeah, I don't want to rat hole on the large block thing. I'll kind of get to why I think large objects are a bad idea, and it's the same reason why Git hasn't seen adoption with things above a certain size. And Git doesn't work for many kinds of things, and there have been many attempts, including IPFS, to level up Git to be able to do this. And so Git, even though it's a very good system for a lot of things, super failed on the dealing with large data, and so that's a mistake that I don't want to carry over. And so I would map, while we can address all of the Git repos natively, and we should do that in a lot of places, I would still like a good implementation of it would map the blobs and chunk them before putting them in, and maintain a mapping. We have to do that anyway for security, because like a good implementation would enhance the security and not rely on SHA-1. And so you would have to maintain a mapping between SHA-1 and SHA-256 anyway, or Blake 3 or whatever you want to use. But that's not to say that we shouldn't leverage the internal structure of new hash functions like Blake 3 to then think of how to enhance the IPLD model to leverage the underlying data structure in that hash function. But we have to do it in a conceptual way that enables other software to deal with the pieces. Because there's going to be a lot of software and hardware that's going to have to deal with fixed buffers that are pretty small. And so you don't want to like disable CIDs from percolating down there. And the block limit comes from that. It's from saying CIDs should be able to go all the way down hardware. And if you don't have block limits, then that doesn't work. But anyway, that's like the summary version. I know that like kicks up a lot of discussion, so I'm gonna move on from here. Cool. So now we've talked about IPLD application graphs. That's kind of what the applications care about. Underneath that, that's where IPLD objects and CIDs and that model comes from, and other tools like car files and whatnot that just are meant to be portable. So this is the layer where most of our systems that we're building are meant to interop. This layer, like CIDs, IPLD objects, things like car files and so on, just formats that just deal with all this, so that as people write more translations of the world of different data structures, the different application data structures into IPLD application graphs, all of the tooling that we're writing just works with all of it, right? If you start targeting case-specific stuff, if you start writing things for like IPLD Git things or IPLD blockchain things, then they won't cleanly work across the stack. And so that's why that barrier is there. And so you should be targeting tools to work with arbitrary IPLD graphs, not with the specific application ones. In general, like of course, there will be a lot of software that just has to target the application-specific stuff, namely that application. But in general, when trying to think of the broader systems, like building gateways or retrieval protocols or browser libraries, service worker things, browser implementations, it should all be working on top of raw IPLD graphs and then materializing that as a second step. This does mean there's a lot of software in the specific IPLD graph layer, but that's where I think WASM has to come in to enable that to be really easy. So you can encode the code itself to know how to use the specific application graph into WASM and then run it everywhere. There's a lot embedded into that, so I can dig into it if useful. Any questions so far here?
I work on content routing and data onboarding. Help me understand this one. Those two IPLD application graphs and IPLD graphs, are they two separate graphs or are they projections of the same graph?
Could be either. In some cases, they're different graphs. Like a Git repo is going to be fundamentally different from a blockchain.
So just so I understand, if I map it to an example, we are saying that the existing Git implementation is indeed an IPLD application graph, but the way that we represent it, if I want to back it up to Filecoin as a car file, it would be an IPLD graph. Is that right?
So yeah, the Git graph is a content address graph. It isn't using CIDs natively. So it as an application isn't an IPLD enabled application because it can't just deal with arbitrary IPLD graphs. It only deals with Git graphs. However, because of how we made CIDs, you can point to it, and you can write applications that then, when you read or write, kind of add the CID magic to enable portability and to use it. I don't know if that answers the question, but.
It sort of does. I guess what I'm.
So for example, like Bitcoin and Filecoin are different. Filecoin uses CIDs, Bitcoin does not. We can point to Bitcoin, and we can take all the Bitcoin data and move it around IPLD graphs, and we can put it on car files, and we can like request it from the gateway and whatever. But when we do that, we have to sprinkle the hashes with some additional information, and we have to create some intermediate blocks, right? So for example, the Bitcoin transaction list you have to create this binary tree in order to get the Merkle root tree, the root of the Merkle tree that's in the block header. And so there's a set of implicit blocks that you have to create. And so if you materialize that into a car file, you get a bunch of little objects that are not in the Bitcoin blockchain, that are implied by the Bitcoin blockchain. You have to calculate them when you use the Bitcoin blockchain, but they're not physical objects in the disk of a Bitcoin node, but they would be in a car file.
So I guess the question that I'm asking relates to the earlier question about efficiency. What I'm interested in learning is at what point in the spectrum, and I know that the spectrum is not fully presented yet, do you see the necessity of changing the format of data on disk? Because there's two ways of representing all of this, right? One is the virtual thing, in that I never change the format on disk. I let people use, protocol buffers or whatever they want to use, and I can project an IPLD graph on top of it at the software layer. Or is there a point here that you see it is necessary to change the bytes written on disk because otherwise we cannot have IPLD graphs?
Clarifying question, by disk, do you mean the software file system of an operating system, or do you mean literally the hardware?
Apologies for the confusion. I mean the bytes that we write on the wire, like the actual
storage,
data.
some kind of data at rest, right?
Yeah. No, I think over time we should endeavor to get as much of that to become content addressed everywhere. However, it's going to be fragmented, and it's going to start as a small amount, and then over time it's going to grow.
Do you see a path where we move towards not changing the formats that people use, but working around it?
Let's zoom out. Like, think 100 years out, 50 years out, 20 years out. Like, will you still have random formats written in the 70s and 80s? Yes, they'll still be around. Will it be wrapped in a bunch of other software to enable it to be compatible? Yes, they already are. And so technology evolves, new formats appear, new ways of doing things improve things, and then you build backwards compatibility. So yeah, we should be aiming to changing the representations. Think about it this way. You can write a pretty high performance operating system, file system, based on CIDs. And then you just run that underneath the hood. And then you kind of, like, then it's totally transparent to the user and the applications. They're just dealing with bytes. But underneath the hood, that's all represented in IPLD graphs. You can do that also with, like, you can take Ceph, you can take HDFS, you can take, like, whatever distributed file systems people use, and you can make IPLD patches for them. You can make either different versions or write some plugins that enable all the data structures to be IPLD enabled. And then it's just transparent to the user, but it happens underneath the hood. Think of, like, the hash linking being such an important innovation that it'll start infecting all of the computing stack, especially as we get into higher and higher performance systems that are, you know, going faster and faster and faster, and need to rely on high security properties. And you can see it today already, even without CIDs. Like, the web is now full of hashes everywhere for integrity checking and so on.
I have a very important clarifying question. I think when you say CIDs, you mean something that most of us do not recognize. Because when you say Git does not use CIDs, what do you mean by that? It totally does.
Git on its own uses just a SHA-1 hash, which is not a valid CID format.
Yes, but
we can map it into
one-to-one.
One-to-one, correct.
Yes. So as long as we can map it one-to-one, and we have
but for example, I can't use a Git piece of software and feed it UnixFS graphs and have it work.
But the same thing is true of, I don't know, of IRO right now.
Yeah, and I think it's a bug. And I've said that. But it's not true of Kubo. Kubo can take a bunch of arbitrary IPLD graphs that you feed it. Maybe not through all of the APIs. All of the APIs don't support that. But the IPLD part of the APIs do. You can, like, feed it whatever graph you want. You can take we've done it with the blockchains. We've taken Bitcoin, Ethereum, Zcash, and others, dumped them into Kubo, shown them through the IPFS gateway, then used the gateway to, like, navigate them. It's awesome.
Well, sort of, right? So, like, the native, it's like, I guess it's like, how much support do you want to give a thing, right? So you know, Kubo will happily take any mapping of any size of, like, CID block, and it will do that. And then once you start getting into, like, the graph realm, where the logic starts living, of, like, how are the things linked to each other? How do I interpret it? How do I follow the links? What is this? Then it starts getting more opinionated, and it says UnixFS.
Yeah, because you're talking about the traversal of the graph, where you need to understand the application to be able to traverse it. Yeah, and that's where I really think WASM is the future and the correct way to do it, where you implement those traversals in WASM and you can run them anywhere.
I think that's fair. I think maybe overarching statement. I think
a very concrete example of what you're saying is today the IPFS gateway does not support WinFS.
Correct.
Bug, huge bug. We should fix that.
Agreed.
By adding, but maybe we should do it with WASM, not by implementing it natively.
Yeah. So I think, like, when I look at IPLD, I think Arkady had a question earlier around, like, what do I think? What's missing here with some of the IPLD things? I think when I look at what we have with IPLD, there's a lot of, like, solid conceptual work, but then there's the number of things that are specs that hit IPLD are sort of fairly limited. Like there's the codecs that map you to the data model. There's selectors which have not gotten a ton of adoption. And there's schemas which have gotten adoption in some places but aren't they don't solve a lot of the problems that people need. And so with other parts of our system, we can look at specs and then we can say, what is the system? The system is this collection of specs which you use whichever ones you would like to use. And IPLD, it's harder to look at that because the collection of specs is sparser. Like there's way more ideas than specs. And I think some of what you're saying, whether it's with WASM or whatever, to do this addressing and pathing and handling the IPLD app graph logic, right? We have no spec in IPLD that handles the app graph logic.
Yeah,
And
to the
that's
point.
probably like a bridge that enables a lot of these applications.
Yeah, we should do that, and and that's where I would severely plug WASM, because that's, you can now safely rely on WASM being everywhere.
Right, but I still want to understand better the Git example, because every single Git object, be it a blob or or a tree hash, it doesn't matter. If you take it and you have the context what this represents, you know how to parse it, you know how to pull the other content identifiers from it. So effectively, it has CIDs in it. Yes, they don't have the prefix,
But they're not CIDs, they're just hashes, which we can
what
turn
is the
into
difference?
CIDs.
What is the difference in your
So
mind?
the difference in the software is that if I go into the Git data structures and I rewrite by hand a commit graph, and I point to a CID of a UnixFS file, or the CID of like a Filecoin block, or the CID of a WinFS directory, it won't work. The Git software won't work.
But the same applies to, I don't know, to Lotus Daemon. The only thing Lotus Daemon will understand from the chain is CBOR blocks and nothing else.
Seems like a bug.
No.
No,
like,
however,
yeah. How would it even
no.
work?
So I think the difference there is not. That's not quite the case, because the state tree can point to anything. The state tree can point to anything, and the deals can point to anything. So now you might want to you have to sanitize the information that goes into the state tree, because that's very expensive space. So you have to narrow down the aperture, but that's kind of like a special purpose thing. So maybe a way to describe it is that the state tree part of a Filecoin implementation is highly opinionated about selecting only a small subset of graphs that are allowed in for security reasons, and then it allows any graphs in the payload sections of the system, right? So a way to say it would be like the underlying guts of the blockchain part of Filecoin are CID enabled, but they don't support arbitrary IPLD objects in that part, but Filecoin supports arbitrary IPLD objects in the data segments, in the payloads. By the way, that constraint will relax as we get scalability. As we get scalability, you'll start seeing things in the state tree that are just arbitrary objects.
But then will every application that deals with this subset of the tree be expected to understand whatever else it is pointed at? So it will have to have UnixFS support, WinFS support.
And by the way, you can take all of those new codecs and programs and put them on Filecoin and make them all addressable. So yeah, it'll be able to understand it. It is not by accident that FVM is a WASM thing that can do that. Yeah.
We should keep going.
Well, Deep, you should probably like adjust the time and give everyone like a concrete time, and you should tell me like when to finish it by, so that.
Well, at the very least, we need to finish the.
This slide would be great. How much do you have after this?
30 minutes.
How much content do you have after this?
Oh, sorry. Yeah, that's what I meant.
How much do you have?
Oh,
What do you
of
ideally?
content.
Yes.
It's just entirely question based, right? Because I could go through this pretty fast. But
Yeah. So Masi, you're the only one left to present after this. Your slides were designed for about 20 minutes, I think, and then Q&A. So I would say, in order to get people after lunch at a reasonable time, if we can do 10 more minutes of this, we're okay.
cool.
Thanks.
So then I'll choose to spend 10 more minutes, and very happy to have another conversation about this later today or in the future. Let's talk about Filecoin data structures for a moment. I divided up the Filecoin data structures into two sets. Different layers of abstraction that should be exposed to different pieces of software and different people. There's the Filecoin user data structures, which are kind of like the deals, the deal payloads, collections, which don't exist yet, but are starting to prop up. And so think of that as like how the applications and the users want to handle their data. Often they will want to point to objects that are defined in some user file system or user database or something, and they'll want to bring their data as it is, and they want to round trip it exactly one-to-one, and that will have to get translated into an app graph, into an IPLD graph, and then put into a payload somewhere. And then you'll have some on-chain data structures that represent that. Here by deals, I don't just mean the current abstraction named deal on the chain, because deals are going to evolve. With more time, I would describe like, when you think about kind of maybe an aggregator, you want to be able to do small writes, and then you want to be able to aggregate those small writes into larger writes. And you also want to be able to have perpetual deals. You want to have a single deal for petabytes or a single deal for exabytes. And the current storage deal abstraction doesn't do that. And that's okay. But here, deal is like the concept of the relationship between the user and the Filecoin system that encodes some connectivity. In Singapore, we had a discussion about the things that we want in deals, in the deal data structures. And we can go through that, can show that slide if we want. The deal data structures goes into payloads, and ideally we want to be able to do collections, especially on chain, because if you have a mutable collection on chain, you can start doing access controls, you can start doing associating deals with that, you can start doing perpetual contracts, and so on. So think of being able to have like very large collections of stuff, like billions of objects, and with mutability, and then having Filecoin deal with the underlying kind of chunking of things and so on. And then the next part is the Filecoin guts structures. And these are specific to Filecoin's internal thing. Think of like this as the inode in a file system. Like the inode in a file system, for very good reason, does not get exposed to the user, right? Can you imagine if you send an email saying, hey, check out this file at this like inode number? Like that doesn't work, right? That's because the file systems were like hard boundary to not do that. In old systems, that did happen. In very old systems, you did have the ability to refer things with the internal file system data structures, and you had computers talking to other computers using that, but they quickly realized that was a bad idea, and then they created a different layer of abstraction. This is why Unix was so successful, because it had path names to then be able to translate between the local addressing scheme and some other remote addressing scheme, and you had path names to be able to reason between them. And it gave you portability across different disks and so on. Portability across different disks. POREP is going to change, and when it changes, it's going to change the proving tree, it's going to change the CIDs, it's going to probably change the hash function, and so anything that you build on top of the proving tree, anything that you build on top of pieces, is going to go out the window. So don't do that. This is one of those cases where I said like years ago, like, don't do that. And people were like, you're wrong. I'm going to go write my software. And I'm like, okay, you're going to have a bad time. And people are now having a bad time, and they're going to have a worse time once the POREP breaks or it changes into something else. And so that's guts data structures. Don't use them. Don't expose them to the user. I know it's attractive and neat because you get the nice property of being able to prove something, and that's really, really nice. However, that's all guaranteed to change. So you could, if you're gonna do that, like you have to build in the fact that the hash function, the algorithms, the sizes are all gonna change. And so you could do that, but like you have to go through the work of like creating this like very abstract thing. It is a goal to eventually do that. Once we have a new POREP, we're gonna be faced with this, and so eventually we'll do it, and maybe we'll have some abstractions you can expose to users. But today, don't expose those gut data structures to users. All right, questions?
Question. Literally what you just said. The hash will change, and so on and so forth. Isn't this literally why we're using CIDs?
Correct. Yes.
So what is the problem to refer to something that will change in 5 years? Just like SHA-256, probably in 10 years will be completely broken. Why is this a problem here, but it's not a problem there?
So if you treat the pieces in the proving tree and so on as just arbitrary APLD graphs, you could do that modulo the problems that Adine found. So we have to fix those problems, and then you can do that. So that's fine. What is not fine is to use not the PCID, but the COMD part of the PCID to then do some like magic expectations with the proving and so on. That's why I'm saying is like dangerous, because there's software being written that expects like this specific POREP, this specific size of tree, this specific like layout, and all of that is likely to change.
So maybe just my understanding of some of the structuring here is that in order for me, a user of Filecoin who's storing my data, to have confidence that the SP has like done anything, right? I need to check the proofs that the chain is producing, which means I need to know some of the
and that's part of the
guts.
Filecoin guts, right? So you have some Filecoin software in your computer checking the Filecoin system, and that's Filecoin guts, that's okay.
So when you say exposing to the user, what you mean is like the actual CID maybe like maybe you don't need to expose the primitive, like the person writing the app developer who's interacting with Filecoin needs to deal with the Filecoin guts. We'll need to consider how that changes and deal with that. But like hopefully the aspects further up the stack need to care less about it because
Correct.
you've abstracted that away.
I would say like expose it less to applications that have nothing to do with that are like layered on top of Filecoin, right? So if it's part of a Filecoin implementation, that's probably fine. If you're going into starting to change other software, some application, like that's where the boundary is. A similar kind of thing here to the other case, we could use WASM to make this fine, to make exposing this stuff okay. But we have a lot of work to do to figure out how we're going to do that and what the abstractions are going to be and what you should use before you can do that. And so we're likely going to end up with versions of the proving tree that are safe to expose to applications so that applications can get the benefits of the proving tree. But that hasn't been figured out yet. So for now, I would say like don't expose the stuff until we have that figured out. And that'll come, that is unlikely to appear before we have a new POREP. Because only once you have 2 or 3 more POREPs will you like wrestle with the problems to then figure out what the abstractions are.
Okay, you can go. No, I have a question.
Oh, okay. So I don't want to eat into Masi's presentation, but I'm going to ask a question kind of about this. So the middle 4 columns are something that I totally understand where you're going with this. I totally understand the value prop. I also understand the cost. Like there is a cost involved in doing the extra work to hash, doing the storing the extra hash and so on and so forth. Like everything inflates by 32 bytes and so on and so forth. And
just remember that userFS OS structure has like 10 layers in.
Yeah, exactly.
That the world added.
Exactly. And today we're in a place, not 15 years from now, but today we're in a place where the middle 4 columns are actually pretty expensive. And we have a number of SPs sitting here who effectively want to be able to sell the thing in the bucket that is only full of the stuff.
Yep.
And they want to skip all this. Like this is the number 1 request. Like, do we have to do all of this? And today I cannot give them a compelling answer.
The answer is yes, because for the software, for the ability to work.
The question is why, not do we?
Yes, I'm trying to answer. For retrievability to work, for this entire system to work that we mapped out, all of the software being written across this very large universe of applications and so on, there's hundreds of companies writing software all over this place. There's like more companies that are going to be writing computing things. There's a ton of software out there. All of it relies on CIDs and IPLD graphs. And so if you want to be part of this ecosystem to enable the portability of the data, you have to do the CIDs. And this is why we baked in CIDs. This is why we have car files, which are obviously like feel wrong to add a car file inside of the sector, right? Like, why couldn't it just be like a normal flat POSIX file? You know, it's like we're introducing the layer of abstraction to get the security guarantees and the properties of decentralized systems. Like we're choosing, like this entire like 10-year set of projects so far is bringing content addressing to the world. And if we skip that, then you dump content addressing out. And so like if you want to do that, like you shouldn't be doing that in Filecoin. There are much faster and better ways to do that. Like if you're just going to do centralized systems, go do it somewhere else. Like go do it in those other networks. If you're going to have decentralized systems, you need hash linking or vector commitments, which is another form of hash linking. And if you're going to do that, then you might as well create a standard interface for them, and that's where IPLD comes from. So it's like a fundamental. It's like core to the stack.
I understand this, but you seem to be mixing two things in the same concept. So you have hash linking, and you have content addressability. They are complementary. They're not requirements to go together, right? You can do content addressability over CompD as it is today, over Blake 3. There is no hash linking in Blake 3 at all.
Yeah, but what other software does that?
Airo.
And what else?
Filecoin to some extent.
No, it doesn't expose it to users.
BitTorrent.
Not on CompD. Not on the literal CompD. No, but which one of these talk to each other? Like, can you take Airo stuff and put it in BitTorrent?
Which one? I don't want to answer that per se because nothing,
No, but that's kind of the point.
Nobody talks IPLD no IPLD application talks to arbitrary other ones. There is none. Like that doesn't exist.
No,
there's a Go stack.
Not true.
Like,
Kubo does it. You can put arbitrary IPLD graphs into Kubo.
yeah, but Kubo's just a file storage system. It's not an realistically, it's not running applications. Yes, there's an IPVM project that is on the way. It doesn't exist yet. There's no compute in Kubo at the moment.
There are lots of IPLD graphs, tons of applications like Ceramic and others who are building on IPLD graphs and can have portability, and they use UnixFS and things like that. And you can take those graphs and put them into arbitrary IPLD stores, and you can put them into Filecoin. That's an example of applications just using IPLD graphs. You can take a Ceramic graph and put it into Filecoin and round trip it out. Doesn't that count?
I mean, I don't want to get, like I said, I don't want to, I'd rather let other folks speak. Because my own viewpoint is that this is very far from reality, of what is available and doable today based on, but I don't, but like I said, I don't want to, I'm not taking a position.
No, but let's consider the alternative, right? So let's consider the alternative. What if we just dump it all out and say, okay, that's fine. Like, let's not do any of this and just go back to user file systems and operating system structs.
But that's not what we are proposing. And actually, no.
You want to use the CompD from here and do content addressing with CompD from here.
Yes.
And how are you going to weave that into Airo and BitTorrent and Ethereum?
You cannot do this with Airo and BitTorrent, but you could do it with Kubo today. Today, UnixFS recognizes UnixFS and raw blocks. Tomorrow, UnixFS can recognize pointers to raw blocks, to CompDs, to BitTorrent, to Blake 3.
What I'm trying to get at is when you start doing that, what you're going to do is you're going to create a parallel set of standards for how to reason about different applications and different trees and different graphs. And that is what that middle set of layers is. So like you will quickly end up adding these additional layers. Like prediction, hard prediction. You can go try it.
No,
Like,
but isn't this exactly what we're building? Isn't this the Merkle forest?
Yeah, but we want to be able to make it translatable. We want software to be able to interop.
So yeah, I think there's maybe like a middle ground here. I tried to cover a little bit in my talk earlier, which is there's a difference between like can and should, right? So like, can I refer to data by PCID? Yes. Should I? Maybe. Depends where, right? If you have your PCID and you're referring to data as your raw block that way, are you going to have a good time trying to convince, if somehow you manage to convince the Chromium developers to take validation of SHA-2 and Blake3 and UnixFS and put that in Chromium, how easy do you think it would be to also get them to take CompP? Maybe not, right?
Pretty hard if you then tell them we're going to be changing this every few years.
Yeah. So this is part of I think the when you choose what pointer you're going to give your user, deciding what that means. But I also think my understanding is that some of the friction comes with the car format, and you can have different formats that still give you CIDs, point to blocks, point to graphs.
And you can have different versions of car files and different, but that's software that goes in there. So what I'm talking about with these layers is not don't add software to the layers. It's just when you add software to the layers, understand what layer of abstraction you're operating in so that you know what's translating to and from and what is the realm of responsibility to be portable. We're trying to enable portability between applications. So if you're going to write software in the IPLD graph section and you only support Git objects, that's not a real thing. That doesn't belong there. That belongs in the layer to the left. If you do that and you're only going to support ComD things, then that doesn't belong in that layer. That belongs in the Filecoin guts. That's all what this is saying. And most software, I'm just stating it as a fact, most software in this broader ecosystem is writing primarily in some application boundary and using the IPLD graph layer to interop with the other stuff. Very little of that software is going to reach further back. Close to zero, but very little of it. Some will, probably, for large, it'll be kind of a power law distribution of some use cases are going to be going to get so much utility out of this that they're going to bake it in, but it's not going to be most of the software. It's not going to be thousands of repos or tens of thousands of repos.
Thank you. Juan, I want to zoom into IPLD graph section in what you have on the screen and Filecoin user structures. I see .car files there. I think on the first one, .car is just an example, right? It could be different things, but as long as it represents an IPLD object, then we can work.
Yeah, as long as it's dealing transparently with arbitrary IPLD graphs, it belongs there. But it has to do that. It has to just rely on CIDs and the IPLD standards and support everything.
Sold. So on the second one, what is the role of .car? Do we mean it to be a concrete thing that is part of the protocol, or is it also another example of IPLD graphs?
Wait, in which part?
The second part, the Filecoin user structures.
Yep. What about that one?
So .car on the slide, does it mean it is inherently part of the protocol, or do we really mean IPLD representation also?
We need an IPLD representation in the deal payload. That's it. It doesn't have to be a car file. You're right. This does not have to be a car file. I put a car file there because that's effectively what the payload is today. But that could be some other IPLD data structure. But if we do that, we need to then understand that if we go away from car files, then we might start breaking a bunch of software. So before we do that, just put some WASM in there so that you can do it portably.
Thank you.
So just in general, we got when you kind of create another way of doing something, you then start splitting the set of things. And if you don't have WASM or something like that, then you end up with a combinatoric matrix of having to implement, for example, the bit swap, graph sync, HTTP thing. Now you have 3 different ways of doing things, and now you have to check compliance with all these 3 different ways of doing things everywhere, because we didn't have the WASM modules yet to be able to just throw in a new implementation in there. So I would just heavily prioritize to make a lot of this much more transparent everywhere and high functioning everywhere, we need to add that portability everywhere. So for example, we need the gateway, we need the Saturn nodes to then have WASM so that they can do the IPLD app graph traversal. Like, that's like high priority.
Good. Any other questions? I think we'll wrap here. It's a good segue, I think, to Masi's content as well, and we can continue discussion through that talk. Yeah, is that okay with you? Juan, thank you very much.
Cool. So just one last comment. Don't worry about the chain size. The scalability of the chain itself is going to end up with a bunch of subnets, and we're going to end up with a lot of new kind of deal data structures. There's a talk recorded from Singapore that kind of goes into all of the different kind of deal data structures that will start emerging. So just go plug for watching that.
Thank you, Juan.